Hi everyone, my name is Harjaap, and in this presentation, Ryan and I will be discussing changes in lipid droplet characteristics after exercise.
IMCLs, or intramyocellular lipids, are fats stored in lipid droplets in muscle cells. Because adipose tissue has limited expandability, fatty acids spill over from adipose tissue into circulation. What results is an accumulation of lipids in non-adipose tissue, like muscle. Metabolically, IMCLs serve as an energy source during muscle contraction, constituting intracellular pools of fatty acids to fuel oxidation during prolonged exercise. In competition with IMCL-derived fatty acids for oxidation are nonesterified fatty acids, or NEFAs, in circulation during exercise. Upon stimulation of adipose tissue breakdown, circulatory plasma NEFA levels increase with exercise, and it has been reported that elevated NEFA levels are able to augment or increase IMCL content and refuel IMCL stores by promoting their incorporation of fatty acids. Interestingly, in endurance athletes, IMCL is dispersed in numerous small lipid droplets, specifically in the intermyofibrillar, or IMF region, of type 1 fibers. This pattern indicates that IMCL is an important source of fuel during exercise. Lipid droplets in the IMF region may serve to deliver fatty acids to mitochondria for oxidation. So, it is hypothesized that IMF lipid droplets would reduce in number and/or size upon exercise. However, in patients with type 2 diabetes mellitus associated with insulin insensitivity, most IMCL is stored in large lipid droplets, predominantly in the subsarcolemmal region of type 2 muscle fibers. Subsarcolemmal lipid droplets are less likely to fuel contraction during exercise, but are still prone to increase in size and/or number because of their proximity to the capillary bed and high circulating NEFA levels.
Damon et al. Had a couple goals for their experiment, out of which we are going to focus on the two that we thought connected most to what we have been learning in class. First, they examined the relationship between NEFA levels and the exercise-mediated oxidation of either glucose or fats and the post-exercise replenishment of IMCL. And secondly, they examined how acute exercise affected the subcellular location, distribution, and concentration of IMCL. Damon et al. Set up this experiment by first measuring each participant's VO2 max to serve as a baseline for fitness. They then told the participants to cycle at 50% of their max VO2 for 2 hours. Glucose or water was supplemented every 30 minutes during exercise and every hour before and after exercise. Blood sampling was done periodically before, during, and after exercise. The blood samples were used to determine metabolic processes that were occurring, and finally muscle biopsies were taken before, immediately after, and 4 hours after exercise. All of these steps are kind of summarized in figure 1. The upward arrows indicate when blood sampling was done. The downward arrows at the top indicate when glucose or water supplementation occurred. Throughout, they did calorimetry, or just indirect metabolic measurements, and muscle biopsies were done in the beginning, immediately after the exercise, and then 4 hours after. The first The first result that Damon et al. Found was that fat oxidation is higher during fasted exercise than when exercising in a fed state. If you look at panel A, you'll see that the y-axis has concentrations of NEFA and the x-axis has the times at which measurements were taken. You'll notice that the solid line, which resembles a fasted state, spikes immediately after exercise and remains higher than the baseline a few hours after exercise. Panel B has glucose on the y-axis and measurement times on the x-axis. The results shown in panel B can be connected to the results from panel A. The trend shown suggests that being in a fasted or glucose deficient state is associated with higher NEFA levels during and after exercise. Panels C and D show the use of fats and glucose by the participants during and after exercise in both fed and fasted states. As you can see with the dotted line in figures C and D, participants that were in a fed state oxidized more carbohydrates than they did fat, and the opposite is also true for the participants in a fasted state.
Next, Damon et al. Examined the impact of NEFA levels on IMCL replenishment post-exercise and in different muscle fibers. In Figure 3b, bar graphs on the left are representative of type 1 muscle, while those on the right represent type 2. White bars are indicative of the fasting state, while black bars represent the fed or glucose-containing state. Graphs D and G represent IMCL content in the form of percent lipid area fraction. Graphs E and H represent lipid droplet size in micrometers squared. Graphs F and I represent lipid number in number of lipids per micrometer squared. Each graph presents the variability in these variables among the baseline, post-exercise state, and 4-hour post-exercise state, or recovery period. Figures D and G present a transient, non-significant drop in IMCL content during exercise, with an increase in IMCL in the recovery phase, or 4 hours post-exercise, resulting in higher IMCL levels in the fasted than in the glucose-fed state. Graphs E and H indicate that there was not a significant change in lipid size between the baseline, post-exercise, and recovery period, while graphs F and I indicate that lipid number increased in the recovery period 4 hours post-exercise in the fasting state. Thus, it would be concluded that the higher IMCL levels originated from an increase in number of lipid droplets, rather than size. Finally, graphs D and G, representing type 1 and type 2 muscle fibers respectively, indicate that the overall changes in IMCL content were detected in type 1 muscle fibers, but not in type 2. This can be expected since type 1 muscle fibers store the most IMCL and are predominantly recruited at exercise with this low intensity. Figure 3a presents the confocal microscopy results of IMCL content restoration at 4 hours post-exercise. With IMCL fluorescently marked, it is shown that in the same individual, the IMCL content is significantly greater during the recovery period in the fasting state, when NEFA levels are high. As discussed in the previous slide, high NEFA levels can augment the synthesis of IMCL content, indicating that fatty acids, not glucose, is primarily oxidized in the fasting state. Directly post-exercise, Damon et al. Did not observe a significant drop in total IMCL content in the study. In the fasted state, fat oxidation rates and plasma NEFA levels were higher throughout exercise and recovery compared with the glucose-fed state. While the methodology used in the present study did not permit conclusions on fatty acid flux through the lipid droplets, it can be deducted that plasma NEFAs in the fasted condition and the resulting increased NEFA delivery to the muscle may refuel the lipid droplets during exercise, hence preventing a significant drop in IMCL. In fact, re-esterification of fat and increased IMCL synthesis in exercising muscle were shown. As expected, glucose levels and carbohydrate oxidation levels were much higher in the glucose-fed state, indicating that carbohydrates were the main energy source in the glucose-fed condition. Furthermore, the higher and elevated IMCL levels in fasted state after 4 hours of recovery were detected when plasma NEFA levels were still profoundly elevated, while rates of fat oxidation had dropped substantially. Jointly, these data suggest that IMCL is restored and LDs serve as a sink to store excess fatty acids. Secondly, it was observed that IMCL content was greater in the IMF of type 1 fibers than the subsarcolemmal region of type 2 fibers. This can be expected since type 1 muscle fibers store the most IMCL and are predominantly recruited at exercise with this low intensity. As such, it makes sense for NEFA to augment IMCL levels in this region, where IMCL fatty acids are primarily oxidized and energy is extracted. However, the study comes with some limitations, especially when it comes to generalizability. The volunteers in the study were lean, young men, and it is possible that other results will be found when studying women. Furthermore, different types of exercise, for example higher intensity exercise, may result in different conclusions regarding the role of type 1 and type 2 muscle fiber stored lipids in exercise.
We had a couple questions for everyone, just to wrap things up. Why would higher amounts of IMCL in type 2 fibers be associated with diabetes when high amounts of IMCL in type 1 fibers are associated with high endurance? Secondly, would someone on a diet low in carbohydrates oxidize more fats or carbs during exercise? And finally, would that same person experience a higher or lower amount of IMCL in muscle a few hours after exercising?